So hello everyone, my name is Pavel and I'm CEO and co-founder of BrnoLogic. And BrnoLogic is a spin-off company based in the middle of Europe, in the Czech Republic. Our company is focused on the area of network packet processing acceleration in the field programmable gate arrays or FPGAs. One of the very interesting use cases that can be solved with the help of FPGAs is the anti-DDoS solution, and therefore we are organizing this webinar today for a larger audience. And I'm really excited to have so many of us here. And now I would like to introduce our keynote speaker. Martin is, as you have probably had a chance to read as well, an expert in the area of high-speed network monitoring and traffic analysis. He cooperates with the state and the private sector on many interesting projects in this area, and not only locally here in the Czech Republic, but also and especially in the international cybersecurity projects. So welcome, Martin. It's a pleasure to have you here, and the floor is yours.
Thank you, Paolo, for introduction. So hello, everyone, and welcome on today's webinar, which is about DDoS attacks, and it's organized by BrnoLogic. My name is Martin Žádník. I work for CESNET as a researcher, and together with BrnoLogic, we undertake research and development in highly innovative projects focused on high-speed traffic processing and monitoring. In recent years, I have become interested in machine learning and hardware acceleration to win the asymmetric battle against DDoS attackers. And that is what I would like to present you today. So let's get on to it. So the presentation is structured into 4 major parts. The first 2 parts of the presentation provides an overview of DDoS attacks and their evolution, while the second half of my presentation is focused on application of artificial intelligence together with acceleration of network traffic processing using SmartNICs and demonstrating the power of their symbiosis on a real-life case. So what is a DDoS? A DDoS attack is an attempt of an attacker to disrupt your business. For instance, if your company offers services over a network to your customers, a DDoS attacker aims to flood either the network or the server resources with an overwhelming volume of traffic. This flood of traffic is intended to render the service inaccessible to legitimate users. So to the legitimate users, the access to the service looks like this. It's not the fault with your connection. Do not reconnect. It's simply how it looks like in a web browser to a legitimate user when the DDoS is effective. The reason behind DDoS is usually to blackmail you. Simply, the attacker wants you to pay them the money for not attacking your company, or it may be your malicious business competitor who pays the attacker to launch the DDoS attack. It's usually during some major event where a lot of your customers, for example, expect you to perform well. Unfortunately, the attacker has multiple options how to exhaust your resources to make your service inaccessible to your users. For example, it starts with botnets, which are computers or devices that the attacker has acquired and can instruct to launch the DDoS attack. The attack can grow in volume using various techniques such as amplification, as well as the attacker has multiple options what kind of vectors of attack to use and what resources to target. As a result, the website under attack then looks like the one on the figure below that you have seen already. Let's dive deeper now into just some technicalities to demonstrate you the various options the attacker has. The DDoS attacks are categorized based on the level they operate at. It could be the network level with the volumetric attacks. The volumetric attacks flood the capacity of the link to create congestion so that the traffic of the legitimate users cannot pass through. Then we have protocol level attacks, which exploit some design feature of the network protocols. And these usually aim at exhausting the operation system that is running your application. Lastly, but not least, there are application layer attacks, and these attacks exhaust the resources that are available, and let's say that they are also assigned by an operational system to your application itself. The source of majority of attacks are compromised devices, such as smart devices you install at your home. For example, one of the well-known cases of DDoS attack was launched from IP cameras, which were part of the Mirai botnet. However, we at the defending side do not always see the original source of the attack due to the spoofing of source IP addresses. The spoofing of source IP address means that the true IP address of the source is replaced with a fake one. In case of the reflection, the source IP address is deliberately replaced with the victim's IP address. In such a case, the bots generate small queries, as you can see on the figure below, and they generate them to the reflectors. And the reflectors answer not to the bots, but to the victim due to the spoofed source IP address. And even worse, the answers are larger than the queries. So the attack grew in volume. And the attacker has achieved not only, let's say, growth of the volume, but also the attacker has hidden the true sources of the original queries, and its botnet is not that easy then to block. Moreover, the reflectors themselves are perfectly legitimate, and they may be even vital for correct function of the internet. So it could be, for example, the reflectors can be, for example, DNS servers, and you cannot simply filter out DNS servers unblock, because a lot of services as well as users would not be able to use the internet itself. Fortunately, there are means to defend against DDoS attacks. For an overview, I decided to categorize them into network-level defenses, application-level defenses, and cloud-based. But that is just my structured view, and there is no formal definition. At the network level, we may apply traffic rate limiting per each protocol. So we know, for example, that DNS, and especially fragmented traffic over DNS, is used for, let's say, creating large DDoS attacks. So we may set up a limit for that. Effectively, what we achieve is that we drop or we limit the amount of incoming traffic at the network level per this protocol. But what will happen if also a legitimate traffic is using this protocol? Then when there is a DDoS, then not only the DDoS packets are dropped due to the limit, but also the legitimate traffic is dropped to the, due to the limit. So we need some more sophisticated means, such as scrubbing devices, to have a more precise tool what to filter. The scrubbing devices usually has some built-in analytics, as well as more fine-grained abilities to filter the traffic, and they are placed in line, usually in the network. Then At the level of routing, still we are at the network level, we can use some routing options such as black holing mechanism, which we can use to actually protect our networks by advertising an IP address that is under attack, and advertising that all the traffic to this attacked IP address should be dropped even before it arrives to our network. So we can advertise this information also to our peers that we are connected to, and they can drop the packets. And the closer to the source of the attack the packets are dropped, the better, of course. Unfortunately, what we will achieve again is that the DDoS for this IP address is effective, and the only thing that we protected is the other IP addresses that are connected through the same link as the victim IP address, and this will not be influenced by the DDoS. So usually the DDoS would flood the link, congest the link, and not only the victim IP address would be under DDoS, but also other IP addresses. And so if we are able to advertise that this IP address is under attack, we can at least prevent the other IP addresses that are not under attack from being not available as well. Then when we go at the application level, there are dedicated devices, usually web application firewalls, for example, to protect web applications. They inspect the content of the arriving traffic and try to filter out malicious requests. However, as we will see during the real case that I will present, is that these web application firewalls may be susceptible to DDoS themselves, so they can create a possible bottleneck. Then I decided to mention cloud-based DDoS protection by leveraging the strength of scaling. So simply, if the application is in the cloud, it can scale to more servers, and therefore when additional resources are needed, for example, as during DDoS attack, then the applications scale, and if the cloud is large enough, then we have, let's say, unlimited number of resources, and we can sustain the high amount of traffic even during DDoS. Of course, for a high cost of paying to the cloud provider. Now we know the defending options. Unfortunately, the attackers know them as well. Therefore, the DDoS attacks evolve to stay ahead. Let's start with the first trend that we see. So in comparison with a situation in DDoS 10 years ago and today DDoSes are very short, and they usually consist of multiple vectors that are running in parallel. So we have multiple DDoS attacks running in parallel, and they are constantly changing every 5 minutes. 10 years ago, the DDoS may have lasted a day or two. Then with TLS encryption, it's very useful for user privacy and authentication, but it makes a defender side a little bit harder, because if we want to inspect, for example, the content of the traffic, then the traffic must be decrypted before the content is inspected, and therefore the decryption device can be, for example, under attack, or an attacker may misuse some TLS features, such as the attacker may require the highest possible level of encryption, thus consuming more resources and so on. Also, with the advent of 5G and edge computing, new vulnerabilities appear. So, for example, the attacker may focus on degrading the latency or the distributed nature of edge computing may be harder to protect due to a missing central view and center point where the protection may appear. So there are new vectors that we will see definitely. Also, the sophisticated attackers aim at lowering the chance of early attack detection as well as they want to evade mitigation. They react upon how effective the attack is, and if it's not effective, they immediately change the vector or change the parameters. Similarly, we have, let's say, not yet seen the direct use of artificial intelligence to actually launch the attacks, but we are definitely aware that the artificial intelligence may serve as a optimizer, for example, of the attacks. So the artificial intelligence may search for the parameters of the mitigation and find out these parameters and then to configure the attack in a way that to bypass this mitigation. So these trends strongly challenge the traditional approach to DDoS mitigation that I introduced earlier. And therefore, the DDoS still remain an asymmetric threat. So we must be ready all the time for an attack that may appear from any direction. Whereas the attacker can choose the time, the place, the resources, so the target, the source of the attack, the technique to use. So it's really still an asymmetric threat. Then we all feel at the defender side that we have a lack of human resources. And especially here, once the DDoSes became shorter, it's really a challenge to respond to them. So we need some fast automated response to either support human or to replace human where it is, let's say, safe and possible. And AI can actually serve for such purpose. And it can serve both for detection and mitigation. So in the case of detection, AI can continually and nearly constantly analyze network traffic patterns, as well as it can identify anomalies that indicate DDoS attacks. To this end, AI can use both unsupervised machine learning algorithm as well as supervised. The difference is that in case of supervised machine learning algorithm, we need annotated data set, which means that we have a data set where we have legitimate samples as well as the samples of the attacks, and we learn a model, a detector or a classifier. We teach it how to detect these legitimate as well as attacking samples. Whereas in case of unsupervised technique, we do not need any annotated data set, and the suspicious events are detected based on a deviance, usually from a normal behavior. So, for example, if there is a sudden peak of traffic that is consisting of, for example, short connections, then this may be an indication of DDoS to happen. And because this is not a normal behavior of a particular application on the internet, then unsupervised machine learning can detect such an event. In case of mitigation, we aim at let's say shortening the time between detection and the action that is taken in the network to mitigate the DDoS. And to this end, AI can help to automate the response. So the AI can either choose what kind of response to take, what's the proper response, what's the most effective, as well as it can really in a short time, in a faster time than in a shorter time than a human analyst can analyze the traffic and let's say pick particular filtering rules to filter out very specifically an incoming DDoS traffic. Of course, at the mitigation side, we must be 100% sure that the result of AI is correct, because otherwise, if there is a false positive, if AI makes mistake, then this mistake is, let's say, reflects on the legitimate users as well, and they may be their traffic may be dropped as well. Of course, in case of DDoS, maybe we are okay if 99% of legitimate users are able to connect, and 1% is dropped due to false positive. Here, out of curiosity, I prepared an example of real-life AI application. I will not show it, but you can have a look later on. You will have the slides. It's a service that is operated by CESNET, and it's nerd.cesnet.cz, and it's a network entity reputation database. And it contains malicious IP addresses and their reputation. And this serves as a proactive defense, not only against DDoSes, but also against other malicious behavior on the network. And you can use it either, for example, as an effective blacklist. So if you select a threshold of the reputation, you can pick 100 most bad IP addresses and have them blocked even before they enter your organization. And actually, the reputation itself is computed by AI using supervised machine learning that is constantly learning from the past behavior of the IP addresses. So it observes how the IP addresses behaved in the past, and if they behave in the future in a bad way as well, then the reputation gets worse and worse. Now let's change our focus on hardware. I would like to introduce you SmartNICs. SmartNICs are programmable network cards, and the level of programmability depends on a particular variant of the network card. It could be either fixed functions, so the functions are pre-programmed ahead, and you can then only use them or not use them, or there are fully programmable FPGA-based, for example, network cards, and you can pre-program them yourself and to meet the demands of your particular application, and then you can use this pre-programmed function. The SmartNICs serve for high-speed packet processing at wire speed using a network card and off-the-shelf commodity server. The concept of SmartNIC and the fast-speed packet processing is depicted on the scheme figure on the left at the bottom. So at the lowest level, we have a SmartNIC, which is able to process the packets at wire speed, 100G, 400G. And then we have a fast packet handling of the packets, usually using some libraries such as DPDK to actually bypass the operation system and to deliver the traffic directly to the application in order to lower the overhead of the software and interrupts and so on. And then we have a software application running in the server. Now let's have a look on the figures on the right. The graph at the top shows the throughput of a certain variant of a SmartNIC based on how many IP addresses is loaded into its match action table. And so what we can see is that around 50K IP addresses, there is a significant drop of performance, more than 100 times. And we need to be aware of such behavior. Because if we need our match action table to store more IP addresses than this, then definitely we will not achieve wire speed. The same goes with the latency, and that is depicted on the graph below. If you are more interested, then please feel free to contact my colleague Paolo Korczek from BrnoLogic to find out more information regarding these measurements. Now, I would like to show the symbiosis between SmartNIC and how can they effectively support the automated analysis, ideally using artificial intelligence. So let's envision a system where we have a SmartNIC and then a commodity off-the-shelf server. And the SmartNIC receives the traffic. Then the SmartNIC selects what samples of the traffic needs to be sent to the software for analysis. Whereas the rest of the traffic remains at the SmartNIC. The traffic or the metadata that are sent to the software are analyzed, ideally using some AI, and then the AI decides what kind of actions should be taken, what filtering rules should be applied. These rules are managed again by a software, so which rule is effective to offload into a SmartNIC, which rule is not effective to offload into the SmartNIC. And SmartNIC only implements the filter itself. So in this case, for majority of the traffic, the SmartNIC serves as a data plane, and majority of the traffic goes just through the SmartNIC, just therefore lowering the latency and keeping the high throughput, whereas only a minority of the traffic goes through the software, or only metadata goes through the software. And this way, software has enough capacity, enough resources to implement some smart analysis. For the smart analysis, that will be the next slide, but for that I will prepare a motivation. by a real case study of an attack. The attack is a really real one, and it was an attack on some major Czech bank. This DDoS demonstrated very interesting vector of an attack. So the bots, as we can see at the figure, were sending SYN packets towards major Czech networks. And at the same time, these SYN packets contain spoofed source IP addresses. But the spoofed source IP address was not randomly spoofed, but it was the IP address of the internet banking. So in some cases, the servers served as a reflectors and responded with SYN-ACK response. This is actually an interesting example because it's not an amplification. In this case, it was a reduction. So we have seen many SYN packets being sent wild into the Czech cyberspace on the servers that were totally not listening for these SYN packets. So majority of the servers dropped the SYN packets, but some of them responded because either there was a service running or out of curiosity, some of them were honeypots, which are designed to answer to anything that is sent to them. Some servers responded, and they responded with SYN-ACK. And at the internet banking, so in front of the internet banking, there was this web application firewall. And the web application firewall was actually flooded with these SYN-ACK packets. The goal of the attacker was to, let's say, confuse the web application firewall in a way that the packets were arriving truly from the Czech cyberspace. So the web application firewall cannot drop the packet based on their source of origin or the link they arrived from, because they truly arrived from a legitimate IP addresses from the Czech cyberspace. And actually what happened is that the web application firewall was not able to sustain that high amount of traffic, and therefore the internet banking that was behind was not accessible. Again, a curiosity is that probably if the web application firewall was not there, the internet banking itself could handle these packets. The internet banking would simply drop them, and it would not be under attack. What's very important from the, let's say, mitigation perspective is not this curious things, but all the SYN packets, so even before the traffic arrived into the Czech cyberspace, all the SYN packets contained a very specific value in their header field. And it was particular TCP window size equal 0. And it's important for, as a motivation for the rest of the topic that I would like to introduce you, and that is automated DDoS analysis using machine learning. So since this attack, we have gone a lot of progress. We've witnessed a lot of progress. We shortened the time that requires monitoring itself of the network, collecting the monitored data, as well as the detection itself. But still there remains the analyst who actually, usually if it's a new DDoS, the analyst has to decide what to do with it. And we need to reduce this time to reaction because we know that the DDoSes are short-lived. So our problem is that we need to create a very specific filter rule that drops the attacking packets, whereas all the other legitimate traffic remains intact. So in this case, in this particular case of attack that I presented before, we would like to automatically infer that drop all the packets where the TCP window size equals 0. How to do that? Well, we can learn under normal condition what is normal, and then during attack, we want to create a rule or multiple rules if it's multi-vector attack to filter out specific DDoS packets. From a graphical perspective, we can, so in the graph, we have x-axis is time, y-axis is bits per second. When there is a peak, there's a DDoS. So during the non-peak time, then we learn what is normal. And then when there is a peak, we sample the peak traffic and compare it with the benign traffic samples that we collected before. In order to do this, our approach is to use machine learning. Specifically, we use decision tree algorithm, which is a very perspective candidate due to its good explainability, because the administrator or the analyst can have a look on the decision tree itself and see how the model decides what's wrong and what's not. Unlike if we have a neural network, then it's very complex network of nodes, and it's very hard to deduce why the network decided to drop or not to drop certain packets. Moreover, it's possible to convert the decision tree into filtering rules, and these filtering rules can be uploaded into the existing filtering devices. It is important to note here that the success of classification is based on two assumptions, that the DDoS packets represent the majority of the traffic mix during the attack. That's usually true. And that the DDoS packets are similar to each other. That is usually true as well. On these slides, you can see the result of the machine learning being applied on a specific DDoS attack. So on the right, you see the decision tree, and on the left, you can see the equivalent filtering rules to that decision tree. And you can see that these rules are perfectly readable. So it means if time to live in the IP header equals 64, then drop the packet because it belongs to DDoS. Or if IP ID equals some weird number, drop it because it's a DDoS packet, and so on and so on. Moreover, on the right, let's have a look on the right. Each node, the first row in each node is the condition how the model decides where to go next. And then we have the Gini parameter, which is a parameter that says how pure is the node. So if the node contains both legitimate as well as attack samples, then it's not pure. But if it's pure, Gini equals 0, it contains only one class, either the attack samples or the legitimate samples. So if we have a pure nodes, then we know that following the path through the decision tree, we can safely, if we have a pure node with an attack class, then following this path, we can safely know that all the packets that will arrive into this node can be dropped. And therefore, we see that now all the leaf nodes of the tree are pure. Therefore, we can trust the model that it will not drop the legitimate packets, most likely. Of course, there might be some small mistakes. And by this, we have arrived at the conclusion of my presentation. So to summarize, the DDoS attacks are continually evolving in complexity and scale. The attackers invent new techniques as well as new applications offer new vectors of attack. And actually, to equalize the asymmetricity of the fight against the DDoS, we need effective mitigation that is high throughput, that enables high throughput, as well as automated analysis and reaction. And exactly, SmartNICs seems like a very promising choice, and they can cooperate very well with the AI analytics. So the smart things can happen at the server side, which is not that loaded due to the SmartNIC. And the smart part can then also use effectively the resources at the SmartNIC to achieve full high-speed throughput of the network traffic processing. So from perspective of a cybersecurity analyst, I am quite positive that we have arrived, let's say, in the state that we have at our disposal a machine brain with programmable network offload. So thank you for your attention. Please do not hesitate to send your question and answers to my colleague. It's korczek@brnologic.com. I wish you pleasant rest of the day and Merry Christmas ahead.
Okay. Thank you, Martin. Very interesting and well done. Actually, we were able to answer some questions during the presentation, and as Martin said, you can still put your questions into the Q&A section, and you can contact us directly at the provided email. But there are more kind of general questions, and one of the most frequent is regarding the speed of the lines we were talking about. So I'll try maybe to answer this. We were talking about backbone networks of providers, and depends on the size of such provider or operator. But generally speaking, we're talking about 100G networks, definitely. And however, as there is still demand for higher capacity, it's all about availability of network devices, and network devices such as switches and cards with 400G network interfaces are starting to appear, especially those cards or SmartNICs with FPGA chips. So the answer is definitely 100G, and 400G is also slowly appearing. And another very often question is regarding FPGA programming, how it is complicated, what all must be known, what tools are used, etc. So if you don't mind, I'll try to answer this as well. So actually, it's not that simple, I think. However, there is no need to start from scratch. FPGA chip manufacturers like Intel or AMD have quite sophisticated development tools available called Quartus and I think Vivado, and as well as a library of reusable components with some demonstration examples. However, not everything is there. For example, you are not able to find there some comprehensive packet processing, but there are also certain open source libraries. We in BrnoLogic use, for example, one open source development framework from CESNET, but knowledge of FPGA technology and its programming is still needed. So maybe this is what we had in mind when we launched the DYNANIC solution. Just a few notes about those. It's a solution that allows you to get rid of the need to learn and program the FPGA while taking advantage of its enormous flexibility and performance thanks to the universal DPDK API. As Martin said, the DPDK is very often used, and this API is also provided with our solution. So if you are interested, you can visit the product page of DYNANIC at dyna-nic.com, and you can find there even this anti-DDoS use case described. So hope this helps. Okay, so let's look to another questions. Actually, there is no questions, just a note about the wonderful session. So thank you for it. So maybe it's time to say goodbye. If you have any further questions, feel free to contact us at this email address or support@brnologic.com. We will send recording, slides, and we will also send some feedback form. So thank you all again. Thank you, Martin, and have a nice Christmas time to all. Thank you and bye.
Bye-bye.